All right, in this section, we discuss our separation of variables for PDEs, which is an interesting process. So it's solving a more interesting type of equation because, well, what's different, first of all, in this section versus what we did before? The equations we solved in the previous section, just to give you an intro about it, just include one term or one separate well, what was that? Okay, one partial derivative term of any order at a time. For this kind of for the equations we're going to solve here, we may have more than one partial derivative term, and well, with respect one variable and the other term with respect the other variable. So the method of solution that we discussed in the previous section is not going to work. So we need a special separation of variables method here. How does it work? Well, first of all, you have to assume a solution of the form u of x y equals the product between two functions, a function of x and a function of y. And if for whatever reason you have, say, a PDE involving x and t, well, assume a solution. Okay, let me write that down. Or u of xt equals to some f of x times g of t. I mean, that just depends on the variables we're given. The form of the solution in the end, it's exactly the same. Assuming a solution in the form of a product of two independent variables. One factor is a function of just x, and the other factor is a function of just y. Differentiate that solution as needed and substitute into the PDE. Separate the variables, and here is where the twist comes into play. Introduce a separation constant since the expression involving x is equal to the expression involving y. Both sides actually must be equal to something, to some constant. You'll see what do I mean. And well, we will often denote this as a constant k, but you can use any number, it doesn't matter. But we're going to stick to k. The previous step right here, by introducing this separation constant, will formulate two separate ordinary differential equations. And you guys at this point are experts in solving ODEs, right? Many methods, although we're going to use separation of variables, spoiler alert, right? So solve the ODEs independently to find the functions f of x and g of y and write the general solution required. Okay, let me show you a baby example first. Okay, so example number one, they're asking us to solve the PDE that's telling us the partial of u with respect x equals the partial of u with respect y, subject to the condition u of 0 y equals to 6e to the 2 y. So, I mean, solving these new kind of equations, we'd better have some condition because otherwise the solutions we get out of the general solutions we get out of this type of equations are really boring if we don't have an additional condition. Okay, well, that's why we have something here. Okay, so number one, assume u equals some f of x times g of y. That is a product of two functions, one function of x times a function of y. What are we going to do here? Okay, take the partial derivatives of this. That is the partial of u with respect x. That is, well, the derivative of big F will be f prime of x times g of y because y remains constant. We're just differentiating the x, right? So f prime, okay, and also, the partial of u with respect y in a similar way, since we're differentiating with respect y, big F of x remains the same. So g prime of y becomes, g of y becomes gy of prime, g prime of y. Okay. Are you guys following me up to this point? All right. Okay, so let's substitute this into the PDE. Okay, guys. So after differentiating, uh, it's fine if you don't write the parentheses x, parentheses y, because when we are setting a solution of this form, should be understood that the first function is a function of x and the second function is a function of y. And also the reason why I'm not going to write this of x and of y, it's to shorten the notation. So this is the same as saying f prime g, and this is the same as saying f g prime. You guys agree with this? Much better, much shorter. All right. Okay. Substitute into the PDE. So let me actually do so. This substitute here. All right. And the number two, this substitute there. All right. All right. Substituting, that's actually, oh, okay. F prime G equals F G prime. All right. So I'm going to separate the variables here. All F's on the left hand side, all G's on the right hand side. So I'm going to divide both sides by F to get F prime over F, and I'm going to divide both sides by G to get G prime over G. All right. And no, guys, we're not going to integrate both sides of this, even though that could give us ln of f and ln of 1. No, because that'll give us independent f and independent g with respect x and with respect y independently. But we want a single solution. So that's why we need to expand the equality and let this be equal to k. All right. That is what we call the separation constant or constant of separation, however you're going to call it. That means, okay, if there is a third party side right here, that means, okay, this side equals to k and this other side also equals to k. Let's write down those two equations separately. On the one hand, f prime over f equals to k, and on the other hand, g prime over g equals to k. These are two separate ordinary differential equations that we can solve by separation of variables. Yes, this time back to the original separation of variables, the week one separation of variables. Okay. What else? Okay, so I'm gonna write 1 over f, this f prime. Okay, here you need to be very careful about what f and g are. While f is a function of x, g is a function of y. So that I'm gonna change the Lagrangian notation f prime into Leibniz notation. This is a function of x. We differentiate with respect x equals to k. And I'm going to separate the variables. I'm going to multiply both sides by the x. So df over f equals k dx. Integrate both sides. And yeah, come on. ln of f equals k x plus, let me call this big C for now. All right? Not a C of y, not a C of t. No, because these are ordinary differential equations. These are actual constants, actual numbers this time. All right? Forget about PDEs for now. Let's focus on solving these ODEs for now. So we could actually integrate. Okay, let me make some room right here. No, not integrate actually. Solve for f by exponentiating both sides. E cancels with ln, and big F of x equals to, you know what to do here, right? E to the kx, it's e to the kx times e to the c, but e to the c by absorption, isn't that just a constant? All right, so that's c e to the kx. All right. Number two, solve the second differential equation here. I know it's the same form, right? But I'm going to go through the entire process here. Yes, so 1 over g dg dy this time, not x, because that's a function of y. And let that be equal to some constant k. Just like before, separate the variables. dg over g equals k dy. Integrate both sides. ln of g equals to ky plus another constant. And I'm not see, I'm gonna use another letter, D. Use the letter D for this, okay? And just like before, why not? Exponentiate both sides. That's g of y. And you know what to do here. D e to the ky. And guys, essentially we have a general solution to the PDE. All right? Okay. Now let's use the space above the second example to finish the problem. So u of x, y, which is some function of x times a function of y, that equals u of x, y, equals to, what was f? C, e to the kx, d, e to the ky for g of y, right? So that's essentially the solution, but we can keep doing even more absorption. So number one, this constant c times that constant d, call it another constant, okay? I'm going to use the letter a, by the way. U of x, y equals to a e to the kx plus ky. So that's actually, guys, the general solution. And yes, even though it's not the traditional separation of variables, actually the solution to the equation looks like that, right? It's just some exponential term. That's all it is, right? However, well, this is the general solution. Let's find the particular solution. That's the fun part, right? That's the most interesting part. All right, what do we have for the general solution? You don't need to flip pages. Let me show you. So we have the condition u of 0y equals to 6e to the 2y. This is going to help us do two things. Find a and the constant k. Okay, now check this out. Let's do it. So with u of 0y equals to 6e to the 2y, what do we do? Okay, again, go to your general solution, evaluate at 0y. That is, everywhere you see the variable x, replace with a 0 and leave the k intact. A e to the k times 0 plus ky. What is u of 0y? Isn't that equal to 6 e to the 2y? Okay, so what does that mean then? A e to the k times 0, which is just 0 plus ky, that's just ky. All right, guys, guess what? Equate coefficients, equate exponents. Check. 6 equals to a, and on the other hand, 2y equals to ky. From the equating of coefficients, we get that a equals to 6, and from the second equating, that we get that 2y equals to ky, which tells us that k equals to 2, isn't it? Now, what does that mean? Go back to your particular solution. U of x, y equals to a, which is 6, e to the kx, which is 2x plus 2y. And that is what? Our particular solution. All right. Okay, so you can see there are some semblances from the beginning of the semester, except that now we're working with functions of even more variables this time, right? So, but the process is somewhat the same. The way we handle these initial conditions is, well, yes, substitute whatever is needed, let it equal to what is given, and then in this case, equate, and obtain the result we're looking for. All right, guys. So example number 2 and last example for this section. Okay, remember that first partial differential equation we looked at the beginning of the previous section? Now we're going to learn how to solve that PDE. That is the partial of u with respect to x minus u equals to partial of u with respect y. With the initial condition or subject to u of 0y equals to 2e to the negative y plus 3e to the negative 2y. All right. Let's solve this problem. Let's solve this problem. So number one, again, assume, okay, so assume some function u of x, y, the solution to be a function f of x times a function g of y, right? That's the form. Okay. Oh, and before I move on through this problem, you can actually take the necessary PDEs, and that should actually be the solution to the equation. You can always verify it. I'm not going to do it for this one, but actually, well, neither I'm going to do it for example number two because we already did it right at the beginning of the previous section. Okay. So what do we need? From here, so partial of u with respect x, that is f prime g. I'm not going to write the x and the y. I think at this point should be understood that the first function is a function of x, and the second function is a function of y. Also, partial of u with respect y equals to f g prime. All right? Okay, substitute into the PDE. Okay, be careful with the substitution. So the partial, okay, let me actually highlight this again. Okay, so the partial of u with respect x, this would be here, isn't it? And then the partial derivative with respect y will be here. What about this u, guys? Well, that's just u without differentiating, which is simply f and g. F times g, I mean. Okay, so f prime g minus what's u? U is f times g without differentiating any of them equals to f g prime. Okay. Now let's play the game of separation of variables. Okay. So it seems like on the left hand side of the PD of the differential equation, well, PD still, we have a common factor of g. I'm gonna factor it out. So that'll be f prime minus f times g equals to f g prime. And well, I guess we can separate the variables from here, don't we? So I'm going to divide both sides by g. Okay, let me actually indicate that. I'm going to divide both sides by fg to have all the variables separated. On the left-hand side of the equation, g's go away. On the right-hand side, f's go away. And check. Isn't that the equation already separated? F prime minus f over f equal to g prime over g. All right. But integrating both sides, that's not how it works. That's the plot twist of the situation. Remember, here is where we introduce the separation constant with the help of this third party constant right here. That's to solve two ODEs separately, independently, and then boom, magic solution. All right. So what do we do? Okay, so number one, I'm going to set, okay, this side equal to k, that other side equal to k. So let's go for it. Let's go for it. So let's solve the first equation. F prime minus f over f equals to k. Okay, guys, before you do anything, yeah, I know what you might be thinking. Multiply both sides by f, and then no. Check this out. F prime over f is just f prime over f. Minus f over f, isn't that minus 1? All right? Equals to k. And then I'm going to write df dx times 1 over f equals to k plus 1. All right? Equals to k plus 1. All right. Well, I'm going to separate the variables for that is the week one separation of variables for us. That is df over f equals to k plus 1 dx. Integrate both sides, and you know what to do afterwards, right? But I'm going to do the whole thing anyway. That'll be ln of f equals to, okay, k plus 1 is just a constant, isn't it? The integral of a constant with respect to x is a constant, k plus 1, x plus, let me call this big C, right? Again, in the end, we're going to absorb all the constants into a single one. Let me exponentiate both sides right here. So f equals, actually our f of x already, equals to e to the c, which is simply c, e to the k plus 1 times x. All right? All right. Okay, so okay, that's the solution to the x equation. The solution to the y equation, what is that? G prime over g equals to k. Even though we already solved it, and just so it doesn't look weird or something. Okay, so that's g prime. Wait. dg over dy this time, because again, the function g, it's a function of y. We already took care of the function of x. Don't forget this g in the denominator. That's 1 over g equals to k. That means dg over g equals k dy. Integrate both sides. All right, integrate both sides. That's ln. Okay, that's ln of g equals to ky plus another constant that I'm going to call d. Okay. And again, just like we did in the previous example and in the previous part, exponentiate both sides. That's going to give us the g of y finally. At this point, that's where I bring back the variable these functions depend on. In this case, x and y respectively for f and g. That is equal to e to the d, which is simply d, e to the ky. Okay. And we're essentially done finding the two functions whose product will be the solution to the given PDE. But again, guys, that's just the general solution. We need to find the particular solution. Okay, that is okay. Well, number one, the solution. So u of x y equals to, again, I'm going to restate that, f of x times g of y. So u of x y equals, what's f? C e to the k plus 1 x times d e to the ky. All right. Again, I'm going to absorb the two constants c and d into just one single one. U of x y, okay, equals to sum a. All right, whatever that is, a e to the k plus 1 x plus ky. So that is our general solution. Okay, let me make this a little bigger. That's too tiny. Okay, all right. So that is our general solution, guys. All right. But that's not what we want. We wanted a particular solution. The solution related to this condition. And right now you're wondering, well, what is that? Well, we're gonna get to see that maybe in the next topic, not right now. All right. For now, let's just worry about the calculus, the integration, the algebraic aspects of the tool. The how to solve these equations. Okay, guys. So number one, let's see. How much space do I have? No, that's fine. Okay. So with u of 0 y equals to all this madness, 2 e to the negative y plus 3 e to the negative 2y. That is the condition that was given. Okay, so how do we work this problem? So because this time we have two terms. Okay, guys, if we were to substitute u of 0 y into here, well, that's going to leave me with one single term right here. However, here I have two terms. That's a little bit of a problem. So in this case, because our initial condition has two terms, we need to solve essentially two initial condition problems, one for each term. That is a case one and a case two. Okay, so let me call this case one, case two. Okay, so let me show you how do we go about these cases. All right, so case one. Case one. Case one is about the first term, 2e to the negative y. So what do we do? U of 0 y equals to a e to the k plus 1. But what's x right here? Isn't that 0? Replace the x with a 0 and then plus ky. Okay? All right. Well, so what do we end up with in the exponent? And that's simply a e to the 0 plus ky, that's simply ky. But what is 0? What is u of 0 y? For the first case, that's equal to e to the negative y. All right? E to the negative y. Okay, so at this point, we should be able to equate coefficients and exponents. So equating the coefficients and equating exponents, we should be able to get a solution. A equals to 2 and negative y equals to ky, where k equals to negative 1. So u of x, y, let me call this u1, okay? Subscript 1 because that's for case 1. All right? That equals to e to the, oh, wait, 2 e to the k, which is negative 1 plus 1 x plus ky, that's k, which is negative 1 times y. That's simply, let me just go about negative y. But what happens here, guys? This is going to go to 0, so this is simply 2 e to the, what is that? Negative y, right? Are you guys following me here? Okay. Case number 2. Case 2. Okay, what is it? So u of 0, y. Okay, case 2 equals to, that's related to 3e to the negative 2y. So u of 0, y, that's again a e to the k plus 1 times 0 plus ky. Okay, so what's u of 0, y? Isn't that equal to, in this case, the 3e to the 2 e to the negative 2y equals to a e to the 0 plus ky. So that'll be simply, okay, again, let me do, oh, wait. That's simply ky, right? And again, guys, by equating exponents, we can get the value of k. And by equating coefficients, we can find the value of a, just like we did with case 1. Okay? So that is a equals to 3 and k, and well, and first of all, negative 2y equals to ky. That means k equals to negative 2. And that gives us, so u sub 2 of x, y equals to, what is that? Uh, 3 e to the, careful, k plus 1, which is negative 2 plus 1, x plus ky, which is actually another negative 2y, which reduces to 3e to the negative x minus 2y. All right. Now we can actually put all these two together. So finally, u of x, y equals to the combination of these two, 2e to the negative y plus 3 e to the negative x minus 2y. Isn't that the same function I gave you to test the very first example, the verify that it is a solution to this same very PDE? It's exactly the same one. So, and again, we were wondering at that point, how do we solve this equation? Well, this is how. This is how we solve these PDEs, right? Okay, guys, an alternative to solve this problem. If you don't want to do this case one and case two, okay, check what you could do. Okay, so let me add one more page. We have time, so I'd rather not start the next section, rather show you the alternative. Okay, so number one, u of x, y equals to a e to the k plus 1 x plus ky, right? That was the general solution to the PDE. All right, but in this case, what I'm worried about is the general solution has only one term, but the initial condition has two terms. We can generate, okay, we can generate two terms out of the general solution because, okay, guys, how did we get A? Remember, how did we get A? It's a multiplication between C and D, right, by absorption. But there's many ways to absorb numbers to get a single constant. We can, okay, what was again the opposite of absorb? We can generate or desorb, maybe? Desorb, is that an actual word? Not into a proof. Again, C and D. We can generate an arbitrary constant by multiplying two numbers, dividing two numbers. How about adding two numbers? All right. How about, okay, let this be equal to, okay, A plus B, okay? E to the k plus 1 x plus ky. And I'm going to generate two terms right here. U of x, y equals to a e to the k plus 1x plus ky plus, what is that? B e to the k plus 1x plus ky. Okay? So okay, if we had an initial condition with three exponential terms, I would need to break up that constant into a plus b plus c. See what I'm saying here? Just to make this potentially more comfortable. All right, initial condition, u of 0, y, that is, replace every instance of x with a 0, a e to the k plus 1 times 0 plus ky plus b e to the k plus 1 times 0 plus ky, okay? So zero of the zeros there, but what is u of 0 y? Wasn't that equal to 2 e to the negative y plus 3 e to the negative 2y equals to a e to the ky plus b e to the ky. And well, if that makes you feel more comfortable, equate coefficient with coefficient, coefficient with coefficient, exponent with exponent, exponent with exponent. Essentially, it's going to lead you to the same result, guys. You see it? So that is, okay. So from here, A equals to 2 for the first term. And okay, I'm worried about the K. Maybe I should have said K1 and K2 because those Ks may not be the same and actually they were not the same, right? They were not the same. So let me call this okay, K, let me call this K1, K1, K2, K2. Okay? Just to be more comfortable with it. Okay? So A equal to 2 and negative Y equals to K1Y. So that means K1 equals to negative 1. And on the other hand, 3 equals to B, B equals to 3, and negative 2y equals to k2y. That means k2 equals to negative 2. Isn't that the exact same result as before? All right. Well, let me just write the function u of xy that equals a, which is 2, e to the, uh, actually, what did we say about it? Just negative y. I'm just going to repeat the same. Plus 3, e to the negative x minus 2y. All right. And that's final answer. All right.